Welcome back. In this lecture, we're going to continue with the case study introduced in our previous video. Now we're going to talk about how to design a study in order to collect the data that we need in order to answer the questions that we're interested in investigating. To remind you where we are from the last lecture, we're looking at a slightly simplified version of the Canadian Trial of Dietary Carbohydrates and Diabetes, or CCD. The primary objective, or our main research question, is, does HbA1c, which is a measure of diabetic control, differ between subjects who consume a high glycemic index versus a low glycemic index diet, where our subjects all have type 2 diabetes and are being treated by diet alone, so no medication. As a secondary investigation, we're also interested in the risk of heart disease. So we'll also compare the level of C-reactive protein, or CRP, which is a marker of the risk of heart disease, between our two diet groups. And we'll be collecting the following measurements on our subjects: their level of HbA1c and of CRP, and for explanatory variables, the diet that they're on, high GI or low GI, and their sex, age, and BMI, or body mass index. We're working through this sequence of steps. In the last lecture, we concentrated on understanding the scientific interests so that we could formulate clear research questions. In this lecture, we're focusing on step 2, designing and implementing a study to acquire relevant data. We won't actually carry out the implementation. That's already been done, and we'll start working with the resulting data, which is steps 3 through 5, in the next lecture. In this lecture, we'll talk about the design issues. By carefully designing a study, we hope to create a situation in which we can make the strongest conclusions possible that will help us understand our research questions. Careful design means that we will be able to generalize our conclusions to a population of interest. It means we'll avoid any systematic error or bias in our measurements or conclusions. It will help us reduce the non-systematic error caused by the natural variability in measurements so that we can get more precise estimates and have more power in our inferential procedures. And it will help us ensure that the sample size is appropriate so that we're not wasting any time or resources by planning a study with insufficient power to see what we want, or a much larger sample size than we actually need. Our first consideration in our study design is what type of study we should carry out. An observational study would allow us to observe subjects in their natural setting, including the diet and lifestyle that they normally lead. This would be interesting. However, with an observational study, we won't know if there are confounding variables or common causes that lead to both changes in consumption of dietary carbohydrates and changes in diabetic control. So we'll choose to carry out an experiment so that we'll be able to attribute to diet any differences that we might see in HbA1c or C-reactive protein. Recall that the key feature of an experiment is that treatments are imposed on our experimental units. Since our experimental units are people, they first need to give informed consent and agree to follow the diet they are asked to. In the CCD study, subjects were provided with some key foods, which were some carbohydrate-rich foods that they were to eat with each meal, and they met with a dietitian who advised them on how to incorporate these foods into their diet in a manner to avoid weight gain. For some of the subjects, these key foods were high glycemic index, and for the others, they were low glycemic index. To summarize this experiment, we have experimental units who are the participating people with type 2 diabetes, and we have one factor, diet, with 2 levels, high and low GI, and these are our 2 treatments. Remember that the principles of experimental design are control, randomization, and replication. And we'll now talk about how each of these was implemented in the CCD study. The first principle of design is to control what we can. In studies such as CCD, one of the ways this is done is through specification of inclusion and exclusion criteria for the subjects to be studied. Remember that our primary objective stated that we would study people with type 2 diabetes being treated by diet alone. This statement already indicates control in two ways. By only looking at diabetics, we're protecting ourselves from the wide variation of HbA1c levels in the population at large. There will still be variation in HbA1c among our subjects, but it's hopefully less, giving us more precise estimates. And this will also help us focus our conclusions. And by only considering diabetics being treated by diet and no medication, we're eliminating having to consider the effect of some subjects on medication and others not. There were several other inclusion-exclusion criteria for subjects to be enrolled in the CCD study. These included age. We were looking for subjects between 35 and 75 years old. Subjects needed to have a body mass index between 25 and 40 kilograms per meter cubed, which are typical values for people with type 2 diabetes. And their HbA1c level, which would be elevated because they were diabetics, still had to be low enough so that they could continue to be treated just by diet. Some of the exclusion criteria, or reasons that subjects would not be enrolled in the study, included if they were taking diabetes-related medication, if they'd had a serious recent medical event such as a heart attack or major surgery, if they had intolerance to any of the study key foods, so then they wouldn't be able to follow the diet, or if they were going on an extended holiday during the year of the study, which perhaps would make it difficult for them to stay on their diet treatment. By controlling all of these factors, we hope to have much less variability in our measurements from subject to subject, and thus much more precision in our estimates. But it also means that our findings will only apply to people who meet these criteria. Another way to control for variation is to use blocking. Recall that blocks are groups of relatively homogeneous experimental units. And by comparing treatments within blocks, we're reducing the effect of that variation that exists between blocks. And that should give us more power for our comparisons. We could have done something like this in the CCD study by using a crossover study. In a crossover study, we would have had the subjects follow one diet for a while, and then have them switch and follow the other diet, with the order randomly determined. This would give us matched pairs data and would allow us to compare the dietary treatments within subjects, reducing the effects of the variability between subjects. However, part of what made CCD a novel study is that subjects stayed on their dietary treatments for 1 year, a long term for a nutrition study, in order to assess long-term effects. So in this situation, a crossover study isn't practical. The next principle of experimental design is the use of randomization to avoid bias. Recall that we can use randomization in two ways: in the selection of experimental units to participate in the study, and in the assignment of treatments to experimental units. If we've done the first of these, that is, our experimental units are a random sample from some population, then we'll be able to generalize our results to that population. If we randomly assign treatments to experimental units, then we'll be able to make causal conclusions. In the CCD study, subjects were enrolled from 5 clinical centers across Canada. Eligible patients at each of those centers who met the inclusion and exclusion criteria were given information about the study and asked if they would be willing to participate. This is typical of how people are recruited to medical studies. The subjects are then not randomly chosen from a population. So we'll have to be cautious about generalizing results beyond the subjects who are being studied. Randomization was used in the treatment assignment. The recruited subjects were randomly assigned to follow either the high GI or the low GI diet. Another way to avoid bias is to use blinding. But for this study, it was decided that it was impossible to conceal from the subjects and from their healthcare providers what the subjects were supposed to be eating, so blinding wasn't used. And the final principle of design, use replication. If a result holds for 1 or 2 subjects, it's not very interesting. We need to see how our treatments work on a large number of subjects to have convincing results. So this leads us to the question, how many subjects should we recruit for our study? Or to put that in more statistical terms, how many observations are needed so that an effect can be detected? That is, that we are likely to get a statistically significant result for a difference between the treatments that we're interested in. This is a sample size question in terms of a testing situation rather than a confidence interval situation. For the CCD study, we wanted to say that the effect that one diet has on HbA1c is statistically significantly different than the effect that the other diet has. So we want to carry out a statistical test. Sample size calculations are related to how powerful we want the test to be. That is, how high we want the probability to be that we reject the null hypothesis when in fact it is false. In order to do the sample size calculation, we first need to know what kind of test we'll be carrying out. We're comparing HbA1c, which is a quantitative variable, between two groups. And we'll investigate whether the mean value is the same in the two groups. So we'll use a two-sample t-test with a two-sided alternative hypothesis, since it's of interest whether either diet has a lower HbA1c mean than the other diet. From our previous study of power, we know that power changes with sample size. To flip that around, we'll calculate the sample size we need to get the power we want. For the CCD study, sample size was calculated to have a power of 80%. 80 to 90% are typical values used in planning studies. Power also changes with the difference between the null hypothesis value of the parameter and a particular value under the alternative hypothesis. In this case, that translates to the difference in the means of HbA1c for the two diets that we think is clinically interesting, so we want it to be statistically significant. For CCD, a difference between the diets in the mean of HbA1c of 0.004 was thought to be interesting from a clinical perspective. Power, and thus sample size, also changes with standard deviation, so we need an estimate of the standard deviation of the difference in the HbA1c means. Based on previous studies, this was estimated to be 0.0066. And power varies with the significance level, or the cutoff for how small is small for a p-value, which then sets our chance of making a type 1 error. And this is often set at 0.05, which we'll use here. Once we've decided on these quantities, we can use statistical software to calculate the required sample size, which I did, and I got that we need 44 subjects per treatment group. Now we expect that some of the subjects will drop out of this lengthy study, so we'll recruit an extra 20%. And 120% of 44 is 53, so we'll need 106 subjects in total. To recap, we've made a number of design decisions. We'll carry out an experiment. We'll recruit about 106 subjects who have type 2 diabetes, being treated only by diet, and who meet our inclusion and exclusion criteria. We'll randomly assign about half of the subjects to a high-carb, high-GI diet, and the other half to a high-carb, low-GI diet. We'll take some basic measurements on each subject, including sex, age, and BMI. We'll have them follow their diet for a year, and then we'll measure their HbA1c concentrations to assess diabetic control, which is our primary interest, and we'll measure their level of C-reactive protein to assess their risk of heart disease. And then we'll compare these measurements between our two diet groups. In the next video, we'll fast forward a year to when we have the data and see what we can learn from it.